Welcome, welcome. All right, in this live coding implementation, we're going to go through a question that came up in the previous session. So we're going to talk about how to implement a stack with queues. And so we're going to briefly go through stack and queue, and then we're going to go and implement a class, our own personal stack, using the queue data structure. So a stack, just to recap, is last in, first out, and it implements a push and a pop, as well as the access, that top function can access that topmost and get the element value from it. And so the queue, insertion and deletion at opposite ends, is first in, first out, and we can see the front as well as putting into the back as well as pulling from the front of the queue. And so it's not always clear how we could implement the top, the stack up here, using queues, because we want to access this rightmost, in this case, rightmost element, which is the top of the stack, and only interact with the top of the stack, whereas the queue has to interact with both ends. And so what we can do is we actually can achieve this by using two queues, and we will use two queues to mimic that insertion into the topmost, or when using a queue, the frontmost spot. So if we have a new item, we'd insert it into a new queue, and then we'd take each of these that are already in the queue and put it in that new queue, so that we'd still maintain that first in, first out order, except we have now jumped a new element to the top of the queue, mimicking that stack last in, first out mentality. So we can jump into our coding area, back into our coding area, and we want to work through our .h, our header file first. So we're going to implement this in three different files: a C++ implementation file for the class, a header file for the class, as well as our main driver program, main.cpp. So our header file, if we think about our header file, we want to use queues, which means we have to include the queue library, and we want to use strings. We'll get to that in a second, but we're going to end up using a string in here as well. And so our queue is going to be a queue of, or our stack rather, our stack is going to be a stack of student identities. And so in that student identity, we want to hold their name as well as their university ID number. And so to accomplish that, instead of implementing a whole nother class, we're simply going to use a struct, and we're going to have the struct of type student, and we're going to put, like I said, the identity number in there, ID number, as well as their name. And so those two pieces of information compose the student struct. Now we can have that data type, a student data type. And so now we can implement our class myStack below, and we're lowercasing it to match our file name here. And so we have our matching of our file name, and we want both private as well as public areas. So our private is going to be our data members, and as we said, we are going to use two queues. We're just going to use the standard library queues to implement our backend, or under the scenes, behind the scenes, under the hood implementation. So our queue is going to be, as we said, of type student, and we want two queues, Q1 and Q2. We are always going to interact with Q1, and that's going to be our primary queue. And then Q2 will just be there when we want to insert a new element. We have to use a secondary queue to insert into that new queue. And so we'll have that to start with. And so we'll do this here, and then we want those core implements. We're only going to do the core functions for a stack. And so we have our void push. And so we're going to push something new onto the stack. And that new thing will be a student. We're going to use prototypes here. We don't need to know the full function header because it's just a prototype. We're in our header file here. So we're defining the function prototypes. We're going to void pop. So we have push and pop for our stack. And pop does not take any parameters, doesn't have any parameters, doesn't take any arguments. And then we also have top, which top will return a student. And we have top, and it doesn't take anything. We also want to implement two other functions. The first is empty. So we return a Boolean true or false based on whether our stack is empty. And the second is our size, and we simply return the size of our stack. So we can have an integer return for that. And this is the core buildup of the header. And so some of these functions we should declare constant, meaning they shouldn't be able to edit the actual queue in the private data members. Specifically, we don't want top. We don't want empty and size to modify anything. We don't want to have that being modified. All they do is return information. So they return information there. So when it's constant declared within the function prototype, that means that any private data members are not allowed to be changed. So this has been our header implementation. So let's jump over to our actual C++ implementation of the class. So we have this class. Again, we're using separate files. And I think I forgot one thing on our header. We use the standard namespace. As always, in most of my implementations, we're going to use the standard namespace. And then in our C++ file, all we have to do is include my stack.h, and then again, using the namespace. So we have my stack.h, which has our header implementation and says, okay, the class has to implement these 5 functions, and it has these private data members Q1 and Q2. So we can go through and implement several of the functions. So we'll save the hardest one for last, which is push, which we thought about when we think about the diagram. When we push, we have that new element, so we have to involve that second queue. So the first couple are fairly straightforward. So int, we're going to use a scope resolution operator to say that we're implementing size. And size will simply return the size of that q1.size. So the first queue is our primary queue. That's everything's going to interact with that. And then we also have our empty call, and we will simply return the value if the q1 is empty. So return q1.empty. So the Q class, the standard library Q class, implements this already. So we just want to pass along that information. Hey, is this empty? Because if Q1 is empty, then our stack is empty. So we have 2 of the 5 implemented. Now we can implement pop and top. So pop and top, pop first. Let's do pop first. So my stack, pop, and we want to take off that frontmost. And by standard, we don't want to, if it's empty, we don't actually want to cause any trouble. So we're going to say if it's not empty, if Q1 is not empty. We can also say that we want to just check whether our stack is empty. So rather than using this, we could say if empty, not empty, we want to pop something off our first queue, our behind the scenes. So if our stack isn't empty, then do something, take that top off. And so we want to take that top piece of information off. So again, we could use either of these. We're going to stick with the Q1.empty. And for the other one, we'll make sure we're not dealing with an empty. So when we go to the top, we want to similarly implement. Oh, that's not supposed to be a return void. We're going to return a student. That struct that we implemented that has those two pieces of information, that's what belongs in our queues. So we're going to say if not empty again. This time we're going to use that specific, hey, check our stack, call our function, not the one specific to our private data member queue. And so this shows both methodologies of implementing that, and we're going to return q1.front. And so we're going to return those pieces, and that's the front function is implemented in the standard library queue, and that returns the actual element value, in this case a student, from the front of the queue. It does not remove anything from the queue, and so the top just gets that value. We would have to call pop if we want to pull it off the queue. So now we've implemented 4 of the 5 functions that we defined in this class. We've gotten pop, top, empty, and size, and we need to implement push. And so push, again, is a void function. We're going to, oops, I'm putting it in the wrong file. Save that. All right, a void function called push, and it takes a student. We're going to call that student S, and we want to push that student onto our stack. And so the first thing we want to do, if we think about back at our diagram, the first thing we want to do, we had a secondary queue, we have Q2, and so we want to take that new item and put it on the Q2 immediately. So we want to push onto Q2 the student S. So all we're going to do is push that student onto S. And so then we have to put all the other stuff that we had on Q1 onto Q2 so that it effectively puts that new student at the front of the line. So we want to go with, while not empty, Q1 specifically is not empty. We want to destroy Q1 essentially. And so we're going to pull apart one by one all the elements off of Q1. So we need to push them on to Q2, and we're going to take the front again, and then we also, in this case, pop. Oops. Okay, so we notice that Q1.front, that's what this does. So we could just call top here. We could call top there, and we could call, oops, I forgot my parentheses there, pop as well. And so we could push the top and then pop off Q2 from Q2 because top returns Q1.front. So we could be using our functions. We're going to simply stick with the more explicit call. And so instead of calling the top function, we will call directly Q1.front. But if we're implementing a class and we know this will work, and we only want to change in one location, we should probably stick with top there. And we should probably use empty here as well. So that calls the empty function, which then goes here. So if we need to change something, we only change it in one location because we're calling this function, and then we're calling q1.pop, which is directly on the queue, q1.front for top, and then within here we want to get that topmost element from q1, which is the same thing as calling top. So here we have the implementation. So we go through our queue and move this element onto Q2, then this element, and so on, all the way through our queue. And we also pop immediately after that push, which means we're diminishing the size of that first queue one by one by one. Okay, so again, we're gonna call empty here, rather not empty, so that we use the decomposition that we've already created, right? So we're already using q1.empty up there. And so while not empty, so everything our function calls will relate to q1. And so this relates to q1, this relates to q1, and now we only explicitly use q2 when we're trying to deal with q2. And so the last thing we need to do is we've set up Q2 to be the proper queue and have that new item at the front. However, if everything deals with Q1, now we have to swap those identities. So we're going to create a temporary queue, student, and assign it Q1, which is currently empty. It should be empty. And then we're going to overwrite Q1 with Q2, and then Q2 with Q1. And so this swap doesn't always seem necessary, right? We're just kind of moving the names around when we have Q2 already assigned, but we want that empty to become Q2. And so, oh, sorry, I have a typo here. We want it to be temp. Temp is that empty queue. And so we have an empty queue here, and we assign into Q1 that new queue. So then when we go back, we've updated our Q2 to be new, and now we've changed its name to Q1 so that when we use Q1 throughout, it's always going to be that queue that has everything in. So when push is complete, this function is complete, Q1 is where the actual data is. And so we've implemented all of our functions now, and we've basically said, okay, push is going to take that longer time. Everything else seems to be short in its implementation and operations count, but push requires us to go through the entire queue, behind the scenes queue, the current stack, and pull everything off and put it back on that secondary queue. So we have those implementations, and now we're going to write our main driver program. Let's make sure some of this compiles first. We don't want to get to the end and oops, didn't actually compile. And so we're going to go through and compile our code, and in the terminal here, we're already in the proper folder, so we can just use G++ and try to compile our C++ file. Okay, so we're going to run this here, and it didn't compile. We have a few errors. That first one, forgot a semicolon over here. Let me save that. And then the second ones relate to that const. So we made those consts, so we have to make sure we put the const in the implementations as well. And so let's clear that out and compile it again. We still have that one control reaches end of non-void function. So non-void function in top there, and we return. So we actually can flip-flop this and simply return the student if it's empty, we can't really return anything otherwise. So we're just going to return in the top, or rather, we're not going to check. There's no, if you call top in standard library implementation, there's no guarantee what will happen if you call top and there's nothing in the stack. So no protections there. We don't need to build them in. The standard library doesn't build them in. It's easier to not build them in, but if you're trying to have a robust implementation of your personal choices, you might want to build in some of those protections. And so, okay, let's clear that out and compile again. And we still have a compilation because this error relates to not having a main.cpp. And so that's going to happen because we're trying to link things together and we didn't specify any flags. So clear that out. We have our main.cpp. Let's implement something boring really quick. And we're just going to, now we're going to use to try to compile all our CPP files. And look, it compiles successfully. So we're good to go in implementing our actual program here, main.cpp. We just don't want to return 0. So let's go about doing that. So first thing, we're going to have to include some libraries. And we're going to include our mystack.h. And so those are the libraries we want to include. We need, since we're going to implement and compare against the STL stack, we're actually going to include the standard library stack as well. And then we need a queue. I don't think we need the queue. We just need those 3 things. So IOStream, and then we need, of course, to use the namespace we want to use. And so we're going to do a few things here. We're going to implement with mystack, right? The implementation that we have. So I'll use mystack. And then we're going to use the STL stack, the standard library. And then we need to have a printout function for that student struct. And we don't need it, but it's much easier and cleaner to print out in a fashion and have that in a function. And so let's do that one first. We just want to print out a fancy printout, print the student name and ID. Oops, autocomplete. So we're just print student, and then we're going to have student S. And so in here, we're simply going to print out the name and the university ID number and some fancy printing, and we're going to separate them by a tab. So when we're accessing a struct, all that information is public. So we simply use the objects that are struct variable S of type student, and then we use the dot operator to access that public data member or data field. And so we have the name, a tab, and then the ID number printed out on a single line. No new line, someone else can handle that. So we're just going to have that print out, and it's not going to use a new line. So now we're going to implement our stack implementation. So now we can say use my stack, and we're going to implement something to actually use our class that we've defined. And so when we want an object of my stack, we'll call it simply STK, and my stack STK. And so let's output some information. It should be empty to start with. So let's check that. And we can compile here and just test out our code to make sure it compiles. It does. And we'll run it. And we see the stack size is 0. And so now we're going to say, as long as the stack isn't empty, print out the top of the stack. So it should not print out the top of the stack because the stack is empty. It's size 0. So let's try that again. And we see that it does not print that out. So we get that printed. Let's clear out some of the printing. So we get back to the top. And now we have our printout that we're going to copy and paste this. So we're going to copy that so that we have it for later. And we're going to do something simple here. And we're going to create a constant integer n, 3, so that we can easily change this during execution and see that it implements this fully. And so we're going to go from 1 to n inclusive, and we're going to iterate. And so each time we're going to add a new student to the stack. So we're going to output that we're pushing onto the stack, and we want to output the ID number. So let's come up with some easy calculatable number for that. And we're going to simply push on that number. So times 3. So that way we'll get 3, 6, 9, and so on and so forth. They won't match the location or the number of item that we put into the stack exactly. So it's a little bit different. And so now we have to set up that struct, that student that we have here, T. And so we're going to choose a name, and we're going to choose a name, Ashley. And we're going to put in our ID number, I times 3 again. We could put this here as an ID number before the output, and that way you use a variable. Let's not waste a variable. Let's do that really quick. And now push T. So we're pushing that student onto our stack and outputting our size. And all of our information. So we want to output our size and our top value and all of our other information that we copied to output, right? So we have this previous output, and now we saw that one's getting pushed on, and now our top value will get output. So let's try to compile that. Oh, we have a few errors. Uint I, a typo. Clear that out. There we go. So now we see here we're pushing 6. We end our program. I forgot to return 0. And we're going from 1 to n 3 times. For some reason it is not finishing. We'll get to that in a second. So we pushed 3, we pushed 6, we went to push 9. Or no, we were pushing 6 and it didn't work out. So we'll get to that debugging in a second. So we pushed it and now we're going to fix out that error that we ran into. Okay, so we're doing a little debugging here. So we have clearly infinite loop because it never terminated our program. This is 1, 2, 3, so something has to be going on. We see we're pushing 6. So when we call push 6, if we go back into our stack implementation, we can try to debug. So we're pushing here, and then if we go back to our implementation, we're taking the top off of the first queue and pushing it onto Q2, and then we call Q2 pop. And so that's where our error is right there. So we wanted to pop off of that first queue and diminish the size of the first queue. So now let's go back to our code. Let's clear that out and compile and execute, and hopefully we see a completed program. There we go. We're pushing all the way through. And now we have all those values pushed, and we're going to then simply output that we're done pushing. So we're going to output that we're done, and so it's a clear differentiation of the program. The pushing's finished, and we have pushing finished. So we have our building of our stack, and then we have our end, and so we can only see the topmost value at all times, so we can't print out everything. We can only print out the top, which is Ashley with a UIN of 9. So we've gone through and done all of that. Now let's start with popping off. So we're popping off the top of the stack, and so we want to pop off the top of the stack, and we have again, we're going to loop that same loop n times, because we put n things in there. We could also simply call the size of our stack. So stack.size. And now we will go through and pop off that many things. And so the first thing we want to do is simply call that pop. And so we want to say, what are we popping? So we want to access that stack, and we're going to access the top value and the UIN. And so that's not a lot of information, but we're simply saying, hey, we're going to pop this ID number off the stack just to represent what we're popping off, to see that. And then we're going to output again our whole size plus the top again. So the same thing we've had here that we're copying and pasting over and over again, the size plus the top value, but with protections, because we don't want to pop and then attempt to print out information on that last time. If the size is 0, we don't want to print out the top value. We don't want to deal with the consequences of not having that protection built into the class. And that's not standard to build in. So we should check first and then get our top value. So again, we're simply printing these out. So we can clear out our print, compile our code. Let me make sure it's saved first, and execute our code. And so we see here our printout. Let me scroll through. We have our print and our pushing. And so now we can have our pop. There we see starting to pop, and then it pops to 9, and then it pops to 6, and the top value is 3. And so now we have that pop that happens when the size is 0. It should be printing. Sorry, we're not including, we want to go to n here. So now our size completes. We want to go to n. We want to pop 3 items off. So if we call size there, it's going to check the size every time, and it'll stop because the size eventually will be smaller than our integer I, our unsigned integer I. And so that we would call first. So we could say size is our stack size. We could do something like that, and then we will see that we complete our program correctly. So let's clear it and compile it. Compile it after clearing. And we go about executing, and so now we have our completion. We see that size 0 at the end for our completion. Everything has been popped off of our stack. And so that's the MyStack implementation. So we can also implement using our STL stack, use STL stack, and it's going to be the same code. So we're going to have the same exact code, so I'm just going to copy it in, except for the declaration. So our stack implementation is templated for our standard library. So we're going to implement a student type here, and then the rest of the code is going to be the exact same. We're just going to go through, and if we actually wanted to check this, we would run our implementation against the standard libraries so that we can check our implementation. So the standard library, all the code's the same except for this declaration. So if we had templated our class, then our declaration would look fairly similar as well. Let's make sure this compiles. It does. We didn't actually call this in our main, so let's scroll up to our main. And then we can call that back to back. Let's put something in our main that kind of differentiates the two, so create some separation here. And we go through and just output some separation there. So clear, and then ./a.out to execute. And so we see what we've seen before. We have our stack up there, and now we're using the STL stack, and we do the same operations. 3, 6, 9, pushing finished, and we're going to pop off 9, 6, and 3. And so if we were to compare these with diff or something, a diff program of some sort, we would get the same results, the same output for both, whether we're using our implementation of stack or the STL version of stack. So in this video, this coding video, we've gone through and implemented a class that defines a stack using the under the hood implementation uses queues. So the standard library queues, and we also used a struct student to demonstrate how to use a struct within a container class. And thank you all for watching, and look forward to the next one.